Dr. Christopher Jones for agreeing to speak for the Science Student Chapter at FAU. He's currently a Bill Guthridge Distinguished Professor of Mathematics at UNC and also a Domain Scientist in the Renaissance Computing Institute at the University of North Carolina. Today's going to be talking about rate-induced tipping and climate, which would be a very interesting topic. I think very interesting to most of the people here who have an interest in applied dynamics and complex dynamical systems. So thanks again, and take it away whenever you're ready.
Alrighty, great. Well, thank you. Thanks for the invitation. And as many of you know, probably I got to know Emmanuel last summer because he was in our summer school that we ran on math and COVID, and one of the stars of the school. So this is a real pleasure to do this. I'm going to talk about rate-induced tipping and climate. I have been interested in climate for about 10 years, but that was only the point in time at which someone pointed out to me that what I was doing on oceanography was really climate. So I guess maybe I've been interested in it for longer. But more recently, rate-induced tipping is something that has caught my attention. I want to explain about that. But first of all, let me talk about tipping points generally. So this is an infographic from a group at the University of Exeter, which is headed up by Tim Lenton, who's kind of very well known in the tipping point area, climate tipping point area, which shows you kind of a lot of the areas in the globe where there is some kind of natural concern for how subsystems of the climate or relevant to the climate may suddenly undergo some kind of tipping, which would be a sort of drastic, abrupt change of state. And this ranges from the polar regions with disintegration of ice to coral reef die-offs and shifts of the monsoons, which would affect weather patterns in Africa and India. And then there's the Atlantic meridional overturning circulation. This is only, I think from my point of view, I think only some of the possibilities. An interesting new aspect has started to emerge with tipping points, which is to do with social tipping points and the idea that we might actually use tipping points in a positive sense rather than a negative sense. And we might even try to engender tipping points. So for instance, we might try to engender the situation where people switch to electric vehicles, for instance, that we might get to a point where it sort of cascades and people change their habits, and we could more quickly go to a carbon neutral world. The thing that sort of interests me about tipping points, I guess, is the fact that this is a place where I think dynamical systems really has something to say, and we're right in the center of this, and they need us. I think if you look at climate science generally, we are perhaps, as dynamicists, thought of as, well, I mean, maybe irrelevant is a bit too strong, but as not in the center of things because so much revolves around big climate models. But I think it's very hard to understand what's going on with these tipping points using big climate models. And I'll even make another point about that soon. So first of all, tipping points, what are they? Well, so it's a rapid change in the climate system or subsystem. It's characterized by irreversibility. There would be some significant impact of that. I mean, think of maybe the, disintegration of the Greenland ice sheet. That would have enormous impact in increasing the sea level by virtue of the amount of water that would go into the oceans. And what we need to do is to understand the triggers, to understand what actually will trigger a rapid change in one of these systems, one of these climate subsystems. And that's sort of what this is about, this rate-induced tipping, because it's a kind of a new idea, an idea that's been around for about 10 years that is somewhat different in terms of tipping from traditional ways in which we think of dynamical systems as tipping. So there's very little in it. The IPCC stands for the Intergovernmental Panel on Climate Change, which writes a report every 7 years or so. I think there's one in the works now, which is, what is it? I can't remember, it's 6 or 7, but they because they revolve so much around the big climate models, they really don't have an awful lot to say about tipping points. This is a picture that I took from the IPCC, which it sort of explains what a tipping point is to a lay person, lay here being non-mathematical, where there's some background forcing that changes, and then in the response, there's a sudden drastic change in the state of the system. And they list the various different things in which they think there's some concern for tipping: the AMOC, Arctic sea ice, glaciers and ice packs, Greenland and West Antarctic ice sheet, vegetation cover. So for instance, the Amazon forest dieback, and various sort of atmospheric and ocean atmosphere regimes like El Nino, the polar vortex, and so on, which are characteristic behaviors of the climate system, which sustain the rhythm of the climate system as we know it. But really, they don't have an awful lot to say about it, because it's very difficult within these big climate models to capture these effects. This is a picture taken from a paper about 10 years ago by Sieber and Thompson. But this is a typical picture about tipping point viewed as in terms of bifurcations. And the cartoon here does relate to climate. So you think of there are two sort of parameter axes here, which will parameterize this surface. And the idea of this surface is that it would represent the state of the system. So each point on the surface is a possible state of the system at the parameter values given in the plane in the bottom. And if you think of one of these directions as a change in the concentration of atmospheric CO2, and the other representing a sort of lumped version of other parameters, maybe. So the idea would be that if you were, say, somewhere down in this area here where you had B, that you could progress up to this point N here as you increase the CO2, and then you might suddenly jump, and this would be a climate tipping point, to another state of the system here. This is obviously a cartoon, and what exactly is being represented here might be something about the entire system. It might be the global average temperature. That's what's being conceived of here. But you might apply this, or think of this picture as applying in some subsystem where this is the increase of atmospheric CO2, but these states of the system are describing the ice cover of Greenland or something, or the West Antarctic ice sheet, its integrity. Now, you might be at other parameter values where such a bifurcation would not happen. So as you increase the atmospheric CO2 along this line A here, so at these other parameter values, you might just naturally and nicely progress up here without a drastic change. Now, there's another aspect here which is important to keep in mind, and that is that every model is inadequate, and one can represent the inadequacy as thinking of the system as being noisy. And we know that noise will also contribute to tipping. And in fact, even in regimes back here, for instance, where you're short of the tipping point, if you have noise, there is a non-zero probability of actually jumping to the other state of the system without having reached this sort of edge of the surface here and reaching the tipping point. So that's another thing. That's what this N here is indicating. Here it describes it as early tipping, meaning before you're reaching the tipping point. So these are known as two types of tipping that can occur, sometimes called B tipping for bifurcation tipping, where you kind of fall off the edge here, where you sort of have, you run out of road in terms of your stable state, and you have to switch to the other stable state because it's the only act in town at that point of those parameter values. And the noise-induced tipping, or N tipping, where you push from one state to another state by virtue of noise sort of just exciting you enough to push you to the other state. Rate-induced tipping is a third type of tipping, and this is a conceptualization of this, which my student Claire Kears, I mentioned at the beginning, I should have mentioned their names, two students who've been very involved in this. Claire Kears, who finished her PhD last year, and Katie Slyman, who is currently working with me. But this was something that Claire came up with, and took me a while to understand why it was an example of rate-induced tipping. And it's to do with this old magic trick of pulling a tablecloth and keeping what is on top of the tablecloth in the same, without disrupting that. All right, so the two states of the system here are glasses of liquid or whatever, a jug of water and glasses sitting on top of a tablecloth on top of the table. And the other state of the system would be those glasses or glass plus jug with liquid in it sitting on top of a table without the tablecloth. So those are the two systems. So if you don't pull it too quickly, what happens, as you would guess here, is, can everyone see that video running? Is that you sort of, you tip all the glasses over, and you also tip over the jug of water. I think that may be one that my student actually made. I'm not sure, because she couldn't find one where it failed. It's easy to find one where it works, right? Because that's the magic trick. And so that is this here. And look at this here at the end of this little science video, where they just pull it, and they pull it quickly enough that the glasses of liquid actually stay. So the rate here is the rate at which you pull the tablecloth, and if you pull it too slowly, you don't get a change of state. You basically just sort of track along with what you would expect by sort of pulling the glass from the jug off. But if you pull it really quickly, you get a change of state. You switch to the other state almost as if you didn't notice it, right? So that's sort of the idea of rate-induced tipping. Let me explain that from a more mathematical point of view. The idea is you would have a dynamical system, and you have a parameter, right? So your parameter here is going to govern the system. And if we think of climate, you might think of lambda as representing concentration of atmospheric CO2. So, but we'll think of that as a real number. X is just in some vector space, some Euclidean space Rn. And the idea is that the this lambda is going to depend on time, right? And so it's going to vary in time, but it's going to vary at a certain rate. So, and we're going to think in terms of that rate, and we're going to want to vary that rate and imagine that rate to be very small or potentially very large, so that this parameter would change very rapidly. Okay, so the idea is that this would be, we'll represent lambda then as a function of r times t, where r is bigger than 0 and r is the rate. So if we write that now as a dynamical system, it becomes a non-autonomous differential equation. X dot is f of x and lambda of RT. And we don't like non-autonomous differential equations. I think if you do applied dynamics, you perhaps learn that fairly on, that's kind of, so you don't really want to look at a non-autonomous equation, and your first instinct is to try to make it autonomous. So we do that by introducing a variable s, which is equal to RT. So then we have at the expense of increasing the dimension by 1, we now have, again, a nice differential equation, right, where the right-hand side is actually autonomous, albeit 1 extra dimension, and the vector field is now 2 things. The first part is the old f, but it depends on x and s, this new variable s, which is sort of representing time, and you get s dot is equal to r. So now r, our rate, is actually a parameter nicely written in the differential equations, and we can think about varying that as part of the differential equations. Okay, so here's the basic setup for rate-induced tipping, and the sort of mathematical idea of what goes on. And the idea is that you want to think of tipping away from a stable equilibrium. And this will sort of explain through this sort of how rate-induced tipping works, and you'll see how it's different from bifurcation or noise-induced tipping, either of those. So the idea is that you've got a stable equilibrium, which is parameterized by your S here, which is in turn parameterizing your parameter that varies in the equations. And we're relating that to time through this S dot is equal to R. But let's just think of this sort of X as a function of S. And we want to think of X of S and lambda of S, think of it as a connected curve. And the idea is that we have a stable path, that this is actually a stable equilibrium, but by that we mean for each frozen S. Okay, so for each frozen S, this is a stable path. But when we vary S in time, so in other words, we take R away from 0, right, we then can destabilize this path. So that's sort of the idea of what can happen here. So it turns out this is well understood if n is equal to 1, so x is in the reals. And here's a picture of that. So this picture is worth spending a little time on because this is the core of it to understand what's going on. Right. So this is my phase space, is the horizontal axis here. And this is my parameter changing lambda. And I've got 3 different fixed points, right? So this is n is equal to 1. So my phase space is just 1 dimension, very simple. I've got 3 fixed points, and 2 of these are stable or attracting. And 1 of them in the middle is unstable. So this is a typical bistable situation. So it might be exactly what you have when you have 2 competing stable states at the same parameter value, and they're separated by an unstable state. Okay, so this is a stable state here, and this is a stable state, right? And we have it for all values of the parameter here between a parameter value lambda minus and lambda plus. Okay, so this is my stable state. Now, if I froze lambda, then I would just take my phase space would be a cross section of this here, right? So imagine taking a line across here. And if I looked at the dynamics of that and I started with initial condition up here to the right, it would just go to this stable state. In here, it would go to this stable state. Over here, it would go to the green stable state. And over here, it would go to the green stable state. You would never go to this state. This is kind of like a threshold that separates these two stable states, or it separates their domains of attraction or basins of attraction, right? Separates the sets of initial conditions that lead to trajectories that go to each of those two states, right? Now we're going to imagine lambda depending on t. So lambda is going to be a function of RT. So if R is very small, this is changing very slowly. And then what happens is if you start the state of the system back here, what happens is you may move away from this thing here, but basically you stay nearby it and you end up coming back to it. So you want to think of here as a sort of there being a ramp function behind this, right? We're starting at this lambda minus, we go to this lambda plus, this is fixed in time, this is fixed in time. And in between, we're ramping up from lambda minus to lambda plus, okay? So if R is very small, you will do what's called endpoint tracking. So you track your system, which is now, you can think of in this two-dimensional phase space, because we've gone to this autonomous system by introducing this extra variable. If we think of this as S rather than lambda now, right, you would end up starting at this state and ending up at this state too, as you ramp from between these parameter values. But what happens if you increase R? So you do this much more quickly. So you go through these parameter values much more quickly. It turns out, and this is a numerical computation here on a particular example system, right, that the trajectory starting here will not end up going back to the same state. It will end up jumping over to here. And notice that there is no bifurcation here, in that as you move the parameter from lambda minus up to lambda plus, there's no actual bifurcation. For each value of the parameter, there are always three states of the system, two attracting and one unstable in the middle. Okay, so this is what happens in one dimension, that you endpoint track for small r, but if you make r large enough, then what you do is you can switch over to the other thing. So there's a theorem underlying this, which is the condition under which you actually get tipping from the x minus to z minus, or x to z, say, okay, from the black curve to the green curve. Okay, so and here's the sort of first result, as a little fact, is that if you take any system like this in one dimension, there is an R0 bigger than 0, so that for all R in this interval, 0 to R0, you do endpoint track the path, right? If we say rate-induced tipping happens, if for a stable path like that, there exists an R0, so that this does not endpoint track the path at that R0. So in other words, if you make R0 bigger, then you do not endpoint track the path. So you get, and we say then that it has rate-induced tipping. So here's a concept which allows you to see when, to give you necessary and sufficient conditions in one dimension when this occurs. And the notion is called forward basin stability. And this is in a paper in 2017 of Ashman, Perryman, and Wieczorek. Sebastian Wieczorek, who's at Cork in Ireland, is I think the person who's really developed this area and come up with most of the sort of seminal concepts. So the idea here is you look at the basin of attraction Remember, this is our point here, depending on parameter. This is the stable point in phase space, and this is the parameter value, a value of the parameter lambda at the relevant S2. And then this is the basin of attraction. Now this depends on S here. So the basin of attraction then, say if you take a cross section here, this is the S corresponding to the lambda here, then the basin of attraction of S1 would be this stuff to the right of the red, and the basin of attraction of S2 would be this stuff to the left of the red. Okay, sorry, of Z rather than X. This is the basin of attraction of the X attractor, right? So the idea here is that if, as you move forward here, you take this value here and you just go vertically upwards in lambda, if for each of those lambdas you lie inside the basin of attraction of this guy here, then you do not have R tipping away from it. But if you get outside that basin of attraction, okay, then there is R tipping away from it. So this is a necessary and sufficient condition. So if this thing bends over enough, so I just go straight upwards from here and I end up in the basin of attraction over here, then I do get R tipping, right? So that's a necessary and sufficient condition, it turns out, right? This is only stated here about there being no R tipping, but you can prove that there is R tipping if forward basin stability is violated. Now, in higher dimensions, this turns out this does not work. Here's an example that my student Claire Kears came up with, and it's basically an example of a bow tie flow where it's not a Hamiltonian system, though. Inside you have spiraling in and spiraling down into the fixed point here. And so you've got two kind of competing, attracting fixed points here, but these are all moving in some parameter space. So it turns out that even though this point here might be in all forward values of the parameter, might lie inside the basin of attraction of this one here, you may still end up tipping away from it if the rate is large enough. And this is a picture of that. So what happens is that even though the point lies in the base of attraction, the trajectory from that point may get outside the basin of attraction. That can't happen in one dimension because basins of attraction are sort of like one-dimensional intervals. But in higher dimensions, there's enough room to move around that you can be pushed out of it. Right, so this is a fairly simple example. We started off with examples in the Lorentz equations and realized that it was just sort of much simpler. You could do it in 2 dimensions. I'm going to mention now a hurricane system. So I'm going to talk about 2 different examples and show you how this actually comes to life. I figured you guys in Florida would be interested in hurricanes. This is a very simple hurricane model, which was put together by Kerry Emanuel and is in a paper in 2017 that he wrote, so it's fairly recent. I have to say that I do not think that Emanuel would thinks of this as a strong physical model that you should really use to understand or predict hurricanes, but he wanted what he called a fast emulator, as he did some risk analysis, and he didn't want to have to run the large computational model, and he found this reproduced the behavior pretty well. There are 2 variables here: the surface circular wind speed in meters per second, that is V. M is a non-dimensional inner core moisture variable, which ranges from 0 to 1. So these are 2 characteristics of a hurricane: the speed the circular wind speed. So how far that's, when you hear about a hurricane and its category, you hear about the wind speeds of, whether it's over 100 miles an hour or whatever. So that's the V. And you also know that, a key is the moisture inside there, so inside the hurricane. So this is a moisture variable. There are two parameters here. One is wind shear. That is the difference between basically the wind at the surface and the wind higher up. And if there is a significant wind shear, it's kind of known that that kind of kills hurricanes. And then VP is a potential intensity. And what you want to think of that's kind of how big how strong the hurricane can be. And you can think of that as related to the kind of heat available to the hurricane from the patch of ocean it's sitting over. All right, this was just a picture that Emmanuel's is taken from Emmanuel's paper, or the Emmanuel Zhang paper, where they compared this model with actual data, and they compared it with a higher dimensional model that resolved much more stuff, which they call CHIPS, the CHIPS model. And this was the red is basically the output of well, this was a particular hurricane in September 2015 that ran from September to October, and to the end of September to the beginning of October. At a certain point in the Atlantic, it's named in terms of its coordinates, and the red shows how it's reproduced by this model, and I guess the black is sort of the best estimate of the track from data, and the blue is their high dimensional model. And this is the wind shear. And this is the potential intensity. So these are the two parameter variables. Anyway, that's just to relate this model to some more physics. All right, it turns out that this is a very nice sort of bistable system, that there are equilibrium solutions for the normalized maximum wind speed as a function of normalized ventilation. This was taken from a paper, the blue from a paper, the red is from a paper by Tang and Emmanuel. The blue is this paper that refers to Emmanuel's paper in 2017 and compares the equilibrium solution. So that's again another comparison. And what you want to think of here is that this upper branch here is a branch where you have a hurricane, and the no hurricane state is the zero state. And that this is some kind of threshold here. So you're in this kind of bistable situation for parameter values in here, say. This is wind shear S. So if there's too large a wind shear, it cannot support a hurricane. So that's consistent with what we know. And the zero hurricane state is here, and as I say, this is the threshold, and this is an activated hurricane. So you would be looking to try to understand what might push us into an activated hurricane state. This is a slightly different value of, well, no, this is actually just, I'm sorry, this is just a blown up picture where this is a little more resolved, it's a little more expanded, I guess. So I'll ask two questions. First of all, can rate-induced tipping cause the formation of a hurricane? In other words, if one of these parameters changed drastically enough, could you form, rapidly enough, could you form a hurricane? And secondly, can you kill a hurricane by rapid rate changes? The answer to the first question in this model is no, because the zero hurricane state is just a zero state. It doesn't move. To have rate-induced tipping, your state basically has to be moving in phase space. Remember, you have to basically, in this forward basin stability idea, get into the basin of another state. Although that doesn't work in higher dimensions, it certainly, you won't get tipping without that. So it is still a necessary condition. It's not sufficient. So, but this is so it turns out you can get use noise-induced tipping to activate a hurricane, which isn't surprising. And that has been shown by Nick Korak, who is a master's student at Wake Forest, and his advisor, John Gemma. We're now putting that together with this rate-induced work. So the answer to the second question is, can a hurricane be killed by rapid rate changes? The answer to that is yes, but it has some surprising features to it. So it turns out what's useful here is that this is a monotone system. A monotone system basically means you kind of preserve some order in n-dimensional vectors. If all of the components are ordered, then you apply the flow and all of the components remain ordered in the same way. So, and a monotone system is known to exist if you have what's called a cooperative vector field. Anyone who studied ecology may know these terms. And cooperative systems preserve monotonicity. So in monotone systems, you get a nice kind of forward basin stability argument. I won't belabor the details here. You have this written down. You can go back and look at it since you're videoing this if you're interested, but you do get, and there's a paper on this in JDDE, which I should have referenced, but by myself and Claire Kears. But with monotone systems, you basically get something like the one-dimensional behavior happening again. So you can get something where R tipping is prevented. So it turns out the hurricane system is cooperative. So you get a monotone system, which is a very nice fact. And these are the two parameters we want to vary. So this is what the picture looks like if you look in the phase space, the VM. Remember, it's a two-dimensional phase space. This is our hurricane state. This is our no hurricane state. And this is our kind of, in quotes, threshold state. So it turns out there you can sort of see everything's kind of rapidly attracted towards this, this kind of manifold here. But what's a key is actually the stable manifold of this threshold point here, because that's the boundary of the basin of attraction of these two things. So breaking forward basin instability means that what we want to do is to get a situation where as we change the parameters, this point here actually ends up lying to the other side of the stable manifold of this point. And you can show that that does happen as you vary parameters in the hurricane system, right? So again, this is how we do it. We add this ds by dt as r. We have lambda is equal to lambda of s. We use that to parameterize both the potential intensity and the wind shear. And so as I said, there can't be R tipping away from 0, 0, but the main result is there can be R tipping away from the active hurricane state down to the 0 state. So you can kill the hurricane, but you have to have both shear and the potential intensity increasing at some point, which is kind of interesting because you would expect the potential intensity. If I go back here to my bifurcation diagram, you would expect something about, you know, the wind shear kills hurricanes. So you would expect that you would need to have the wind shear increasing to kill it. But this is killing it without pushing it over the edge here. This is still within a regime where you can sustain an active hurricane. But the surprising thing is that you also have to increase the potential intensity, which means that you have to increase the amount of fuel, in a way, the heat available to this hurricane, which you would think would enhance it. But there's kind of a conceptual thing here. It's a phenomenon that the problem is you're requiring the hurricane to be stronger. And it may not want to be stronger with that wind shear. It's more vulnerable to the wind shear if you try to make it stronger. So this is a picture of how that works. This is the 0 hurricane state. This is in the phase space. The green is the active hurricane, and this is the threshold, the unstable state. You endpoint track if the rate is too low, but as you increase the rate, you start out close to the green and you actually end up getting pushed down to the 0 hurricane state. Right? So this is the picture in the phase space as lambda varies. So that's what happens with a hurricane system. Second example I want to talk about, and I'll just go through this quickly, is the carbon cycle. And this is another two-dimensional model, but this one is not monotone. The previous work was done by my student Claire Kears, and this was done by Katie Slyman, who's my current graduate student. And these are her slides. And so this is about understanding the carbon cycle, in particular in how CO2 is absorbed by the ocean. And absorbing CO2 in the ocean causes acidification. This is roughly the cartoon of that. There was a recent paper by Rothman in 2019 in which he came up with a simple dynamical system model for the marine carbon cycle. It's simple, but it hides a lot of stuff inside these sort of functions here. I'm not going to go into the whole model here, but these are the C and the W are the various kind of developed variables relating to the chemicals that tell you whether there's how much carbon there is in the ocean and so on. And so, but let me talk more about the mathematics here, since I don't want to spend too long on this. So depending on the parameter regime, it turns out you get a stable fixed point, a stable limit cycle, or possibly both. What's interesting to us is where we have both, right? Now, this is a bistable situation, but one of our stable states is actually a limit cycle, a periodic orbit. Nu here, you should think of this variable nu here as representing the amount of available atmospheric CO2. So we're interested in how changing nu affects the outcome over different timescales. Now, this is not a model that is intended to represent something over, decadal timescales. When one talks about the carbon cycle in the ocean, you often think of sort of paleoclimate timescales. So, thousands of years rather than decades. So, it's questionable how much this would apply to the modern situation, but nevertheless, it is a good cartoon of how the carbon cycle works. So what Katie determined was well, this was actually sort of Rothman talked about this, that, if nu is big enough, that this could lead to significant disruptions in the ancient Earth system, right? So he left this kind of rather provocative question about pointing out that we're now near an equivalent threshold, and are we headed therefore for a mass extinction? That's a tongue-in-cheek, but I think he said that in the paper. So will our tipping occur? So here is the phase space. Here is our stable state. This is at certain parameter values here. Now our intermediate state here is our threshold state, is this sort of unstable limit cycle or unstable periodic orbit, where you spiral down to the stable fixed point inside and spiral out to the stable limit cycle outside. Okay, so that forms the boundary between the basins of attraction of the stable fixed point and the stable limit cycle. So it turns out in this case here that, because of the sort of simplified geometry, that there's a result like forward basin stability that basically works here. And what you have to see is whether, as we change parameter values, this guy here can actually get the other side of the threshold, which is to say, can it get outside this limit cycle? So this is a picture of the unstable limit cycle here at the bottom, and the fixed point here is these dots. So it starts out in this configuration where this is well above the limit cycle. And now as you move down here, right, both the stable fixed point here can go down, and you can find a set of pairs of parameter values for which the stable fixed point is outside of the unstable limit cycle at a further developed parameter value, which is exactly what you need for rate-induced tipping. So here's the statement. So we wanted to jump from the fixed point to the stable limit cycle. We take this ramp function here and we let R vary. So this is ramping between lambda minus at minus infinity and lambda plus at plus infinity. So S dot is equal to 1 here. You take S actually equal to T, not RT. So R is actually inside the parameter nu here. That's just the way that Katie set this up. And this is the picture that sort of shows you what happens. So this is developing R. The top left-hand side is R equals 0.1, and then you move across to the right, and then you go down to the next level, 0.4, 0.6, right? So this is with the ramping in there, and this is seeing what happens to the trajectory, which you initialize at a fixed point at the lambda minus, the beginning of the ramp value, to the fixed point at lambda plus, the end. So if the rate is too small, you start at the lambda minus fixed point and just end up at the lambda plus attracting fixed point. And this happens for a while as you increase lambda. You start seeing sort of more spiraling here rather than kind of going straight to it as your R increases. And then here's one where you really go through quite a lot of spiraling before you this. And then suddenly, I mean, this spiraling is somehow associated with getting closer and closer to this unstable limit cycle. You actually end up in the situation where this is outside the unstable limit cycle for the more evolved parameter value, and you get tipping to the stable limit cycle. So this does happen in this Rothman model, which says that, you know, if your increase of atmospheric CO2 is too rapid, then you can jump from the stable state to the unstable state. Okay, so let me just wrap up. Conclusions. So these monotonicity conditions give a natural generalization of the one-dimensional phenomenon of rate-induced tipping. So this is well developed in one dimension. There was some work in higher dimensions, but we kind of gave that some kind of clarity with these monotonicity conditions. The Emmanuel hurricane emulator is monotone, and a hurricane can only be formed by noise-induced tipping, but it can be killed by increasing wind shear and potential intensity. R-tipping also occurs in the Rothman model and shows that increase of CO2 could trigger a jump to a different state. I didn't discuss this, but similar results hold for a basic energy balance model of Earth's radiation. This was also in Claire Keir's thesis, and if anybody's interested, she wrote a very nice college math journal paper for undergraduates around this idea to help teach the greenhouse effect. Other contexts of relevance that we're interested in, polar vortex and other situations like that. We're working with a group on trying to see if a simple model of the polar vortex can see triggering going on with some kind of rapid change. I mean, so the idea is that, you know, the rapid change may be afforded by increasing atmospheric CO2, but it could be some intermediary thing that is changing rapidly because of the change, or the more gradual change in CO2. So it may be the fact that we're having, say, warmer summers, and that associated with that is maybe a rapid increase in the temperature in spring or something. So that's a manifestation of global warming, but it's the more localized rate change that is actually triggering the effect of interest. So, okay, I think that's all I have to say, and maybe I'll stop sharing my screen, and if there's any discussion or any questions, I'm happy to talk. Oh, there's something in the chat. It'll be nice to have the links in the chat section. Oh, okay. I'm trying to think where the links were, but we can extract the links from the talk. And actually, what I could do is send you a PowerPoint of the talk, and then you would have the links.
Thank you very much. Let's all thank the speaker. And yes, thank you. Are there any questions that anyone has?
So you alluded to the fact that you'd looked at least a little bit at what happens in Lorentz. So I was kind of curious about when you go from 2 to 3D, is some of the intuition helping here for looking at higher dimensional, say even 3-dimensional cases, or how much work has been done?
That's a good question, actually. So, and I don't really have a good answer, actually. We just sort of played with the Lorentz equations as an example, and we realized we could get that example in 2D. Let me see how much has been done in 3D. This idea of sort of jumping outside periodic orbits has been developed by Pete Ashwin and a student of his called Hassan, and they have some nice, actually they're calling it P-tipping. They have a recent paper that I think was just put on the archive, which I think that stands for phase sensitive tipping. So you get, the effects just start getting more and more complicated. I mean, we've made efforts at trying to develop a general theory, but it gets pretty difficult, I think. So, I think that's sort of an open area.
But so you would have a periodic orbit and it's attracting, and then you have some other bistability, so maybe some other attractor, and you're looking at if you can jump from one to the other?
Yes, right. So instead of in that Rothman model, my base state was a stable fixed point.
Mm-hmm.
I suppose that had been a periodic orbit. In fact, suppose I'd been talking about jumping from that outer periodic orbit. Then you can imagine, it depends where you are on that periodic orbit in relation to the changing configurations of the basins of attraction as the parameter varies, that is going to be relevant. And that's one thing they do and they talk about. But where you have, so if for instance, an interesting thing with the Lorentz equations might be in a pre-chaotic state with the Lorentz equations, you can be in the situation where things look kind of nice, but if you look at the stable manifold of the saddle point of the Lorentz equations, it's horrendous, right? It's very kind of, that's the work of Hinke Osinger and her, where she's crocheted the stable manifold, where you probably know about that, James, I think, right? So,
sure.
And I think that would be kind of interesting, because there you've got your boundaries of the basins of attraction are extremely complex, even though the basic states themselves look kind of tame.
You have transient chaos near these attractors.
Near those, yeah. Right.
Thanks a lot.
Yeah.
Other questions from anyone? I have a question. Some collaborators and I have been thinking about a phenomenon that's exhibited by some hurricanes called rapid intensification. This is sort of, from what I can tell, it's kind of arbitrarily defined change in maximum sustained wind speed over some chosen time interval. So it exhibits a large change in intensity over a short time span. And we were approaching the problem from a very different kind of perspective, looking more at prediction models, statistical prediction models using satellite image features of hurricanes. But I wonder if you could speak to rapid intensification, if this is a phenomenon you've thought of in terms of tipping points, or if it's a feature of the simple model that you discussed earlier.
I don't know. That's pretty interesting, actually. Yeah, that's a good point. So, so this is where you would go from a sort of category 1 to a category 5 very quickly.
Right. Yeah.
Right.
Yeah.
Right.
Like I think it's a 35 knot increase over a 24-hour period is how the scientists characterize it. But in some cases, hurricanes exhibit much larger changes over that same time period than even that. And it's becoming more and more frequent, an event that we see in hurricanes.
So my guess is sort of the message from what we found, and again, this is on a very simple model, right? So, but the message I think would be that as that happens, the hurricane is more vulnerable to other things like the wind shear. So the sort of stars would have to be well aligned for that to happen. Whereas it might have, if it intensified more slowly, it might have survived some anomaly in wind shear. That anomaly could kill it if it tried to rapidly intensify. But I mean, that's off the top of my head. But that's pretty interesting. So, has anyone done any work using bigger ocean atmosphere models?
Yeah. So
rapid intensification.
Yes, I believe so. My understanding is that the kind of parameterized models are notoriously poor at accurately predicting these kinds of events.
Right.
And so people have turned to statistical models to try to make predictions about the likelihood of rapid intensification taking place.
Mm-hmm.
And that's been the more recent push for developing models that could be used to predict these events.
So are these, yes, I mean, are you doing, how is the data? Are you doing like machine learning with the data to get the models, or is that?
Yeah, so some of the published results are simpler than you might consider machine learning models. They're just like logistic regression models on collections of features that are known to be important in characterizing storm intensity, extracted from different kinds of satellite images or reconnaissance measurements.
Right.
And then, yeah, you can develop probabilistic models, simple models like logistic regression. We were thinking more along the lines of using machine learning applied to images, like and really extracting dynamic changes in cloud structures in order to try to predict these things. And so the data we were using, much of the time is spent curating that from geosynchronous satellite orbit databases that have high temporal and spatial resolution images of storms.
So the goal would be to look at environmental conditions in some future storm and try to predict whether it's vulnerable to, likely to undergo rapid intensification because of the various other factors. Yeah.
Exactly.
Do you know, has Emmanuel looked at that at all? Do you know? I mean, he's missed, I always think of him as Mr. Hurricane, but he's not a name that appears in that literature. Kerry Emmanuel.
Well, I'm no expert.
Yeah. Okay, that's all right.
So
I just wondered if that came off the top of your head, if you'd seen his name in that. I mean, he was using this fast emulator in a sense for sort of statistical purposes, for risk hazards. I mean, he wanted to assess the basically the likelihood of a hurricane actually reaching the coast of the U.S., the east coast of the U.S. You know, how many hurricanes reach the east coast of the U.S. And if you have a model that actually resolves these hurricanes, that's pretty intensive model, I think. I mean, I don't think they can really do that at this point. So, and that's a similar motivation to yours for looking at statistical model. Yeah, lots of interesting stuff.
Yes. Other questions? Maybe one more if anyone has it. Otherwise, we can thank Christopher again for a very nice talk.
All right, thank you. Thanks, guys. It was fun.
Appreciate
It
it.
was nice meeting you all. Great seeing you again, Emmanuel, James.
Yeah, thanks a lot.
Also-
Thanks a